Okay, so we're very happy to have Dempsey, who is a finishing graduate student here at Princeton, working with Silvio Buffo and me and others. He'll tell us more about Adjoint QCD2.
Great, thank you. Yeah, thanks for the invitation to present this work here with Igor, with Silviu, and with Benjamin Sogard. And I'll be telling you about a numerical method, the lattice Hamiltonian formulation for two-dimensional adjoint QCD. If you're getting some deja vu, that's because 2 years ago at the inaugural workshop for this collaboration, I also gave a talk on numerical methods for small n two-dimensional adjoint QCD. But there's, despite appearances, there's been a ton of progress since then by many people, including in the room. I'll be talking about, of course, this Hamiltonian lattice formulation, which is a numerical method of a very different character and gives us some new results and capabilities. There's also stuff I'll mention in passing. There's been Monte Carlo lattice simulations of the same model. George Bergner, Stefan Pamonte, and Mitat. Uwe Trittmann wrote interesting papers on improved DLCQ methods and illuminating some of the insensitivity to the number of colors that we observed in this prior work and in this new work. Alexei and Maria computed the beta functions of 4 Fermi couplings that are ever interesting. So lots is happening. For the few members of the audience who have not worked on this model, let me give a brief review of it. So this is going to be two-dimensional gauge theory. I'm going to take the gauge group to be SUN. Almost everything I say can be ported to other gauge groups, but I'm just going to take SUN for simplicity. And then we couple it to an adjoint Majorana fermion with some mass m. And this model has really 3 very surprising features. One of which is has a mass gap at n equals 0. This is not generic of two-dimensional gauge theories. Joma Gomez and Diego and Matthew Yu gave a nice classification of theories with this property. Adjoint QCD is a large family that has this property. Most interesting for this collaboration is that when the adjoint fermion is massless, the model is surprisingly in a deconfined phase. You would not normally expect adjoint fermions to be able to screen interactions between, say, fundamental probe quarks, but this is the case when the adjoint fermion is massless. And finally, as Fedor was just telling us, there's a sort of miraculous supersymmetry that comes in when you tune the mass to some particular value depending on the number of colors. So these are all really neat things, and we'd love to have a way to have some non-perturbative approach to this theory. So that's what I'll be telling you about. So that's adjoint QCD. Let me motivate some Hamiltonian lattice formulation. So Fedor told you a lot about DLCQ, which is another method that's been used for this theory going back to the 90s. And it is a great method, and it gives us a lot of interesting things, including, so far, the most precise estimates of the masses of bound states. But it has some severe limitations as well. One of these is that we don't have really access to the ground state, so we can't measure observables like, say, the fermion bilinear condensate. That's one limitation. Another is that it's not really known right now how to access the topologically non-trivial universes using the light cone quantization method. Not to say that it's impossible, but it's not really known how to do it. And so that's one thing the Hamiltonian lattice is able to do for us, in addition to getting us the vacuum state. So in addition to these advantages relative to DLCQ, the Hamiltonian lattice has some great advantages as a lattice method. One is that I'll tell you about the staggered fermion prescription. That allows us to avoid fermion doubling, which is usually a real headache for lattice gauge theory. And as Martin was telling us, these Hamiltonian lattice methods have current potential for quantum simulation for, say, the Schwinger model. And in the future, hopefully, we can simulate models like this as well in real time and be able to simulate collider processes and all sorts of interesting things like this. That's still far in the future for this model, but it's a neat possibility. So before we get into the adjoint QCD, I just want to talk about the setup for the Hamiltonian lattice formulation of the Schwinger model. I'm not going to talk about Schwinger model physics. I just want to show you the lattice setup so we can do the adjoint case by analogy. So in the Schwinger model, we have this U1 gauge theory with the Dirac fermion and some mass m. And we want to put it on the Hamiltonian lattice. So we're going to be discretizing space and leaving time continuous. So we'll take this Weil gauge prescription that Martin was telling us about, fixing A naught to 0, and we can write the Hamiltonian for this model. We have some gauge kinetic term, a fermion kinetic term, and a mass term for the fermions. and E of x here is the conjugate to the spatial gauge field, and it gives us the electric field. Good. So in addition to this Hamiltonian, it's all important to include the Gauss law in this Hamiltonian prescription. The Gauss law in the continuum tells us that the divergence of the electric field was given by the charge density, and also invariance under large gauge transformations tells us that this E of x will be integer valued. So let's take this Hamiltonian now and discretize it. So what we're going to do is follow this Kogut-Susskind prescription, where on the sites we're going to have the particles as always, and the staggering prescription is that we'll take the upper chiral component and put it on even sites, and the lower chiral component and put it on odd sites. That's how we spread out the degrees of freedom of the fermion. And on the links, as always, live the gauge fields. And so we get a picture like this. These chi variables are related to the size by some rescaling related to the lattice spacing A. And so we have these chi's staggered on sites. Between them are these gauge fields UN. Right. And so then the lattice version of the electric field will be these Ln operators. Okay. So in terms of these, the Hamiltonian is going to look as follows. We have a gauge kinetic term, which counts the energy of electric fields. It's going to look very similar on the lattice in terms of these Ln variables. There'll be a fermion kinetic term, which, using a particular gamma matrix convention, is going to look like a hopping term on the lattice. And then finally, the mass term. In the U1 case, there's this important mass shift. If you're in New York, Grisha told us about the mass shift that we looked at for this model. It's very important to understand how the chiral symmetry works on the lattice. I won't say too much about it here, since Grisha told us about it already. But then, very importantly, we have this Gauss law, which we have to port to the lattice as well. And so it's going to tell us that the difference on the electric fields between two neighboring sites is given by something related to the fermion occupation number on that site. But what we have to do is have this staggered shift, which, for instance, you can motivate by having charge conjugation symmetry. But it's sort of what leads to this mass shift, is this staggering. This is important to the U1 case and not as much for the adjoint case. So I won't say too much about it here. But the most important thing is that all this business that I'm highlighting here comes from one-site translations, which interchange the chiral components of the fermion and tell us about how chiral symmetry works in the lattice. So I will come back to that for the adjoint case. All right. So let me just show you what the gauge invariant states look like in this model, because that's what we really need the analogy for the adjoint case. So what we need to do to satisfy the Gauss law is to have the sum of all these charges, which I showed you on the previous slide, add to 0, simply because if I add up this equation going all the way around a periodic lattice, I have to get 0, and that's the sum of the QNs. So that tells me that the gauge invariant states for the Schwinger model are going to be half-filled configurations of these fermions on each site. And so I can write down some arbitrary half-filling state. And then you can compute the QNs and see how Ln changes on each link. You get some profile like this. So as long as you know where L started, you get everything else from the Gauss law. And so this is very useful. You can see from this that all you really needed was this picture, right? Once you have the Ln's on each link, you can use the Gauss law to back out what the fermions were and figure out everything else you need. So the most important physical picture is just what these Ln's are. And we can think of these Ln's as telling us what the representation of U1 is on each link. A picture we'll come back to in a little bit. All right, so that's the Schwinger model. And then if there's no questions here, I'll move on to...
I would say that, you see, in the way I view it, A0 equals 0, it's not a real choice of gauge, because A0 is Lagrangian multiplier normally in continuum, and you always can re-express it in terms of other field. When you say numeric value, you mean in this procedure like you are describing, that you have kind of condition on all this, but it means that it was complete gauge fixing. You need to fulfill this Gauss law, right? Absolutely. I mean, and that's what they are describing. No, maybe it's phenomenological, but I still, I don't know. You can maybe say that on the lattice A0 and 1 is the same. I'm not sure about this. So because we are saying that Hamiltonian. Once you said Hamiltonian, then A0 is different from A1.
I agree. A0 is rearing its head in the form of the Gauss law here, for sure. So it's not, we haven't, you can try to shove it under the rug, but it will come back exactly in this way. Yeah, for sure. Yeah. Good, okay. All right. So let's move on to the adjoint case. So it's going to look very similar. We have a gauge kinetic term. We have a fermion kinetic term, which looks like a hopping term. And the mass term looks a little bit different. That's because we have Majorana fermions here, but it's actually looks more similar to the fermion kinetic term in this case, but with an alternating sign that makes it different. So we've really just sort of dressed the former Hamiltonian with a bunch of adjoint indices, these capital A's and B's, that enumerate the different components of the adjoint fermion. But the Hamiltonian has a very similar character to what we had in the Schwinger model. The Gauss law, also very similar. We have a difference between Ln and now an Rn. R is sort of the right side version of L stood for left. R stands for right here, and this is related to the fact that we have a non-abelian gauge symmetry now. But morally, it's the same. The electric field changes by something related to the charge density on each site. And so this is our Gauss law. And so we have a few key differences from the Schwinger model. One is for the links, right? We had gauge fields. You can think of them as particles on a U1 manifold on a circle. That was not too hard. Now we have particles on an SUNC manifold. That's a little harder. And the second thing is that the gauge invariance condition are going to be harder to implement, again, for the reasons of the non-abelian symmetry that we have to deal with now. So I'm going to describe now how we can set up the space of fermionic states, the space of bosonic states, and how to form gauge invariant states out of them. All right. So first, let's talk about the fermions. So on each site, we're going to have an adjoint, nc squared minus 1 fermions for the adjoint representation. But that means it's going to be many more actual states in the Hilbert space, right? I can take these, if I take, say, 2 sites, I can pair up these 2 Majorana adjoint fermions to form one Dirac adjoint fermion. And so you can just count that the number of states there is going to be 2 to the power of nc squared minus 1. All those states have to organize somehow into representations of the gauge symmetry, the SUN living on each site. And so you can do a group theory exercise, and you can show that that what happens is that those 2 to the nc squared minus 1 states are going to organize into a product of these 2 copies of this representation R with some multiplicity. R is going to be the representation. You can describe it in many ways. Its highest weight is the Weyl vector of the group. Its Dynkin labels are just 1, 1, 1, 1, 1. Its Young diagram is this sort of staircase thing. And so it gives you a definite representation for any SUN group, or actually any group. So for SU2, this happens to just be the fundamental, the spin half representation. For SU3, it happens to become the adjoint representation. These are 2 low-dimensional coincidences. For SU4, it's the 64-dimensional representation, which is just some other representation. I don't know of any other significance to it. But this is how these states, this is how these fermionic states organize into representations of the gauge symmetry. So we have lots of copies of this representation R, 1 per site. And so if you want to look at all the fermionic states, I can just say, okay, on each site, I have some state in the representation R with some index for that representation, these M's. And then I also want to keep track of the multiplicity coming from this multiplicity label here. That won't be so important for the discussion, but it's there and it will be along for the ride. So that's the fermions. Let's now talk about the bosons. So we said that we went from having a particle on a U1 manifold to a particle on SUNC. And so here's sort of the analogy on how to go from the Schwinger model to this adjoint model. In the Schwinger model, we had wave functions on a circle on U1. Of course, we know the wave functions on a circle, a good basis for them is e to the I n theta. And the energies of these are going to look like n squared if you work out the gauge kinetic term. Now, a way to say that is that we took all the representations of U1, which are, again, e to the I n theta, and the energies are given by the quadratic Casimir of the representation, which in that case is just n squared. That story works and can be carried over to SUNC. There's a math result, the Peter-Weyl theorem, that says that if I want a basis for the wave functions of a particle on SUNC, I can take the matrix elements of all the now higher dimensional representations, irreducible representations of SUNC, and that the so the energy term for this representation is going to be again related to the quadratic Casimir of that irreducible representation. So that's how the math ports over to SUNC. And so the sort of takeaway when it comes to gauge invariance is that now when I look at the space of bosonic states, I'm going to have indices for all these representations, arbitrary irreps of SUNC, that we've chosen on each link. So lots and lots of indices floating around. And so if we want to make gauge invariant states, we're going to have to contract them all. So let's look at how to do that. Okay, so to build gauge invariant states, we said we want to choose an irrep on each link, these little r's. These are arbitrary. On the sites, we had a specific irrep, which is this capital R, which we said what it is for each group. All of these are going to be carrying indices of the gauge symmetry. We have to contract them all to make gauge invariant states. And so we have for each site, for each copy of SUNC, we have 3 indices, one from the one each from the 2 neighboring links, and one from the on-site representation of the fermions. So how do we contract 3 indices of 3 irreps of some group? We have to use the Clebsch-Gordan symbols to tell us how to fuse 2 representations into a third. And so the way to build our gauge invariant states is going to be by contractions with all these Clebsch-Gordan symbols. That's how we can build something that is invariant under the large SUNC to the power of the number of sites symmetry. So these are going to be our states. And so you can construct a Hilbert space out of all the ways to organize these irreps on links like that. Good. And so we can write down some basis, right? We would label the states by representations on each link. Again, those multiplicity labels, which are along for the ride. And we're going to get some very large space of states this way. So let's look at some examples to make this a little bit more concrete. So I'll show you examples for SU2 and SU3. There's going to be a key difference. So this representation R, we said for SU2 was the fundamental, and for SU3 it was the adjoint. Well, for the fundamental for SU2 changes whether you go from integer spin or half integer spin representation. And this is, we can say this in fancier language, that the NCality is going to be changing by 1 between links for SU2. For SU3, it's the adjoint, and the adjoint has NCality 0. And so there's not going to be this sort of staggering per link. So let me show you the example so I can describe what I'm saying here. For SU2, we could have a link that starts with a spin 1, and then on each site, we have to tensor with a spin half, and we can go up or down, just with the SU2 tensor product. So I can go up to 3 halves, up to 2, back down to 3 halves, up to 2, up to 5 halves. There's, of course, many choices, but this is one of them. But you can see this alternation. On even links, I have integer spin representations. On odd links, I have half integer spin representations. For SU3, it's sort of similar. I can start with some representation on this first link, and then I keep tensoring with the adjoint. So 1 times 8, there's an 8. 8 times 8, there's a 10 in there, so on and so forth. I can keep tensoring. I have to keep track of multiplicity in this case for NC greater than 2, which is an annoyance, but it's fine. But the key difference here, all these representations have 0 NCality versus these alternate site link to link. Good. And so, but if I go 2 links over, in either case, no matter whether NC is even or odd, I'll maintain the same NCality. So that's sort of the group theoretic kinematics here. Now, in relation to the discussion we were having just a little bit ago, this whole Hilbert space is going to split up into many subsectors. And they're labeled by, we can say, the NCality on say, the even links, which we said was going to be the same. So for SU2, this is an example of the sector or the universe, we say, in which the NCality on even links is 0. I could have another universe, which you could imagine just sort of shifting this over by 1, where the NCality is 1 on those even links. For SU3, there's one universe where I start with a singlet here. I could also start it with a fundamental or an anti-fundamental, a 3 or a 3 bar. Those would give me 2 distinct other universes or other sectors for this theory. So that's how these sectors all line up. Good. So that's how we see this on the lattice. Now let me talk about that one-site translation.
So the two sectors for SU2 is integer fractional versus fractional integer fractional.
Exactly, right. And so for in the SU2 case, it's a one-site translation that would take you between these two different
They
types
are
of...
interchanged by shift by one lattice spacing, which also interchanges bosons and fermions. So that's what Mithat was saying.
Exactly, I'll come to that in a moment, yeah.
And the total number of lattice sites has to be even in those cases. So.
Yeah, we're just looking at
Yeah, I should have said at the beginning. The number of lattice sites will always be even in this case. Good. Yeah, so let's talk about one-site translation, as Igor was just mentioning. So the continuum model has this Z2 chiral symmetry, where we take the fermion side, a gamma 5 times side. And so in the Schwinger model, this one-site translation, as Grisha said a couple of days ago, is related to a chiral symmetry. Likewise, in this model, a one-site translation is going to be related to that Z2 chiral symmetry. And so we notice a difference in the previous slide between the NC odd and NC even cases. When NC is odd, the one-site translation does not change the universe, right? So if I took that SU3 state from before, moved it over, I still have NCLD0 representations on each link. Versus when NC is even, like for SU2, a one-site translation would change the universe. I would go from the integer, half-integer universe to the half-integer, integer universe. So this is a key difference between these two cases. So what is this telling us physically? We have this one-site translation. It's related to chiral symmetry. In some cases, it changes the universes. In some cases, it doesn't. The fancier way of saying this is that these universes are distinguished by a ZNC one-form center symmetry. So this is a symmetry which tells us which universe we're in. Now, for even NC, there's going to be a mixed anomaly between the center symmetry and the chiral symmetry. So that means if I act with this chiral symmetry in the form of doing a one-site translation, I'm going to change what universe I'm in as distinguished by this center symmetry. So this is sort of the underlying mathematics that the lattice is realizing for us in a nice way and showing us this mixed anomaly precisely when it's supposed to be there for the case of even NC. This was computed before by Alexei and Mithat and others, and we're seeing it now on the lattice. So let me say a few more words about these mixed anomalies. We can actually use our lattice model to uncover all of them and compute all of them for the case of a general group. And we see that when we take the group to be SUNC, which is the case that was computed before by Alexei Mithat and Theo Jacobson and Yuya Tanizaki, we see a nice agreement in that case, and we can extend the computation to other groups. So for instance, there's a mixed anomaly between the fermion parity symmetry and the chiral symmetry. We were just discussing this about how this is related to a boson fermion degeneracy that you can see in this model. I won't say too much about that, but this is the story from before. And there's also charge conjugation, or in more general groups, autonomorphisms, which have a mixed anomaly with the chiral symmetry. And then, as I was just telling you, the center symmetry with the chiral symmetry. And the nice thing in that case is that the mixed anomaly here comes down to a property of the representation R. And it's relatively easy just to do an explicit computation of this representation R in any Lie group, and just ask what happens when you do this one-site translation relative to the tensor product with R. And you can enumerate all the cases where you get this projective sign. SUN with even n is one case. There are others, including E7, in case you were curious. So it's a neat thing we can get from this model. Good. So now let me go back more towards sort of explicit things we can do on the way towards numerics with this model. So if we want to actually implement this Hamiltonian, actually construct it and diagonalize it and get results, we're going to need some way to represent these operators, the Majorana operators on each site. We're going to need to know how they act on the gauge invariant states. I don't want to go too much into detail on this because I'm running low on time. Let me just say that we have these chi's, they live on sites. They carry an adjoint index, but on the sites there are also this representation R index. Right, each site carries representation R. And so if we're going to act in a group, in a gauge invariant way on the gauge invariant states, we're going to need some objects that carry an adjoint index and two indices for the representation R. We're going to need these invariant tensors. And so you can ask, how many are there? It turns out this very nice answer for SUNC. There's going to be NC minus one of them. For example, in NC equals 2, the adjoint is the adjoint, and R is the fundamental, and so you only have one invariant, the Pauli matrices. For SU3, it's all adjoints, just as a coincidence. And so what are these invariant symbols with 3 adjoint indices? Well, it's your F and your D symbol for SU3. You can extend this to arbitrary NC and show that there's always NC minus one of them. And so this motivates a really cute ansatz, which involves some Majorana fermions that are different, these sigmas that carry the multiplicity labels, which I don't want to go too much into. Well, let me just say, this ansatz is nice, it's cute. There's really no guarantee that it should work. There's some consistency condition that these invariant tensors have to satisfy for this to work. Super non-obvious that this can be satisfied. I don't know how to prove it. But in all these cases we've checked, SU2, SU3, SU4, even G2, we checked SO5. Miraculously, this condition is satisfiable. So there's something really nice about this ansatz. It seems to give us the answer. It'd be nice to know sort of the deeper group theoretic reason why, but that's an open math question. Anyway, it works, in particular in SU2 and SU3, which are the only cases we can do numerics for. So let's just run with it and see what we can do. Yeah, we have this representation of the chi's. We have all the gauge invariant states. We can just grind out the Hamiltonian and make some real big matrix. And the point of this slide is to tell you how big it is. So if I want to do even a modest 6-site lattice for SU3, and this is a parameter that tells me how many representations I allow to live on the links. It's some cutoff for the formally infinite Hilbert space. For some computations, we really need to go to 20 or so. In that case, we're going to need a 13 million dimensional Hilbert space. So it takes some elbow grease. But we can do it. And so let me show you some numerical results coming from both SU3, which I've shown you here, and SU2 as well, which is significantly easier.
B is the universe?
Sorry, yes, P is the universe, yeah. So, right, exactly. So it's comparable numbers for the different universes. Yeah. But we can target any individual universe just by choosing which representations we have on the links, which is a nice advantage over DLCQ. So speaking of DLCQ, I mentioned before that DLCQ really only gives you easy access to the topologically trivial universe, the one where you have no sort of background flux tube in the theory. And so that corresponds for SU2 to really only being able to access positive M when you work through all the mixed anomalies we were talking about. It really only gives you positive M. And so from before, from what I told you 2 years ago, we had these points in orange that give you the DLCQ mass at the lowest fermion state as a function of the mass of the adjoint. Now with the Hamiltonian lattice, we can extend that to negative mass, which corresponds to going to the non-trivial universe. And we can see that there's a nice zero crossing right here at minus 0.56 or so, which is about minus 1 over root pi, which is negative the value that Fedor was telling us about in the previous talk. And so what this corresponds to is we've taken the supersymmetric point in the non-trivial universe, and there's going to be spontaneous breaking of the SUSY by this background flux tube. That gives us a massless Goldstino mode. And so that's what the lattice is nicely picking out for us here. So this is some really nice physics that we're able to see relatively easily with the Hamiltonian lattice. Good. More about supersymmetry. Again, as Fedor was telling us, we can take m squared to be NC, in this case SU3, so I have a 3 here. Difference in normalization between us, but we have a 2 pi here, but it's meaningless, it's just a normalization. This is exactly the mass Fedor was telling you about. And we can see if I take this real big Hamiltonian, diagonalize it, and look at the fermionic and bosonic states in red and blue respectively, we see them nicely lining up in this small L region, and this is for n equals 6 sites. So if you take the lattice, try to take L too large with only 6 sites, eventually you're going to have like really large lattice spacing. You're not really anywhere near the continuum theory, and so this is not sort of a physical regime. It's this small L region where we should expect to see the supersymmetry happening, and there it is. As we take the number of sites larger and larger, that region would extend further and further along this plot. So we're seeing nice evidence of what Fedor showed us just a moment ago. Good, what else can we do? Well, in the beginning, I told you DLCQ can't access the vacuum state, so we can't do things like compute the fermion bilinear condensate. With the Hamiltonian lattice, we just directly get a state as the lowest energy state for the vacuum state. We can look at any correlator we want. In particular, we can look at this fermion bilinear condensate. And as Michat and other authors nicely showed in their Monte Carlo lattice paper, if you normalize this expectation value by the Chuff coupling and by the number of adjoint fermions, you see this nice behavior where this is for SU2. We see it coming down to this value minus 0.087 or so. Now let me show you SU3. Yeah, basically the same. So it's a really nice instance of that same insensitivity to the number of colors that we've talked about before and ways written about, where even for 2 and 3, where the expansion parameter 1 over NC squared is quite different, 1/4 versus 1/9, we see this near exact Chuff scaling, which is a neat observation. And this is reflected also in the spectrum. Other observable, this is just a new observable that also obeys this nice scaling. So this is very neat. I should say in gray, by the way, orange is the numerics. Gray is a strong coupling expansion with the lattice, which is a way to do some exact calculations, not having to diagonalize giant matrices. And you also do quite well if it's observable with this lattice strong coupling expansion. But I won't say more about that in this talk. Good. So that was, we covered the supersymmetry, which is one surprising feature of the model. We covered NC and sensitivity. Now, how about deconfinement? We said that when the adjoint fermion is massless, we should be able to see deconfinement. We should see the string tension going to 0. What that should mean is that if I have a string of fundamental flux around my periodic lattice, that is, if I go to the p equals 1 universe, it should have the same energy as the p equals 0 universe because that flux tube has 0 tension. So we can just directly compare the energy of the p equals 1 ground state to the energy of the p equals 0 ground state and see how close they are. And that's what we're doing in these plots, subtracting those two energies as a function of the circle length. Now, again, we're a very small number of sites. We can only go up to 6. But you can see a nice progression as we increase the number of sites from 2 to 4 to 6. The region over which the string tension is roughly vanishing increases steadily. And so the expectation is that if you go to the n equals infinity limit, you would just get a flat line all the way out for any circle length here, which is nice. And we can do the same thing with antiperiodic boundary conditions.
These are without the 4 Fermi deformations.
That's right, yeah. And so, exactly, thanks for bringing me to my next point. This works really well, almost surprisingly well, because there's all this nice work about the 4 fermion couplings that can be added to this model. And we have not added them explicitly, but you might worry that the lattice would add them of its own accord. And so you might think you might have to tune those couplings so that in the IR they go to 0 and we reproduce this behavior. We didn't have to do that, sort of surprisingly. And so it's a neat question why that happened. It could be that we generate them with the appropriate signs such that the beta functions that Alexei and Maria computed tell us they go to 0.
I think actually, based on discussions in New York a couple of days ago, I think they cannot be generated with the right power of lattice spacing, so they just wash out, and it's just a hunch.
Cool. Okay, we should discuss, but yeah, we need, yeah. Hopefully, there's a good explanation. Maybe that's the one, but it's a neat question. All right, good. If I have a moment, then I'll tell you about one more thing. If we take the fermions with antiperiodic boundary conditions and we give a small mass to them, so we're moving away from that point where the string tension or the universes should be exactly degenerate. Yes, indeed. So as Misha and other authors showed us in 1995, you can do a very nice instant calculation and say how the trivial and the fundamental universe split when you turn on a very small mass. And it turns out to be exponentially small in 1 over the circle length. So on a small circle, you should see a really small splitting between these two energies. You might worry that the super small splitting is going to be hard to see numerically. I certainly worried this. Turns out, no reason to worry. If you just run this lattice, here's a log of that energy difference as a function of 1 over the circle length. We see a beautiful exponential scaling with exactly the slope that Misha and friends predicted back in the 90s. So 30 years later, we can actually do the computation and see it. This is for SU2.
Wait, what? Sorry, I didn't understand. What are you plotting now?
Oh yeah, so this is this exact same energy difference computed with instanton effects. Now we're just taking on the lattice, we're computing the ground state energies in these two universes, subtracting them, and
When the mass is small, it's not exponential small. That's not true.
So it's GL.
it's exponential in GL.
GL is.
It is
Linear
compactified in a
mass.
circle. There's
Ah,
a
you're
linear
looking
between-
at the compactified here?
Yes.
Yes.
We're only doing small circle.
Small circle.
Yeah.
Small circle.
Yeah.
There is a holonomy potential.
Yeah, yeah.
It has a minima. These are the instantons
Yeah,
related.
this was
But the
the
splitting
initial
at small
state.
mass has nothing to do with instantons. There is a splitting already at infinite volume.
Well, yeah. So at infinite volume, there's a splitting proportional to m, as you guys computed. But yeah, on a small circle, there's this exponential suppression.
Right.
Yeah. So this is just this is an observable we happen to be able to compute well on the lattice, so we did it in a small circle regime, and in that regime, yeah, we see this exponential scaling with this. So this black line is fitted to the intercept, but not to the slope. The slope is from Misha's calculation, and it agrees precisely. And we can do
So
this.
we coupling calculation in small circle.
And so we can do the same thing for SU3. Again, the black line is with a slope generated by Misha, and then the orange points are from our lattice, and we see a beautiful agreement. Good. So this is one more nice confirmation that our lattice really is reproducing the expected effects of this model, and that we can do new things with it that we couldn't do with previous methods. Great. So let me wrap up. So Hamiltonian lattice gauge theory, as has been mentioned several times in these two workshops, can be a really powerful tool for studying 2D gauge theories. And here we've really pushed it to a really interesting non-abelian model, this adjoint QCD model, which has all these very interesting physical effects that we'd like to explore more, and we have a new tool for it now. And so in the future, we have lots of things we want to do. We want to generalizing to more flavors of adjoint fermions, looking at some of the other models Federer was discussing. There was a nice paper on this recently from a group in Belgium, looking at the two-flavor case and its phase structure. On the numerical side, there's all sorts of nice tools we'd like to apply: tensor networks, DMRG, the quantum mechanics bootstrap. All these might give us new capabilities to go to more than 6 sites, which would be nice. In addition, there's the 4 fermion deformations, which we've talked about already. There's some interesting physics there, and how these relate to the non-invertible symmetries that Zohar and friends have discussed. Also interesting questions for the future, but I'll stop there. Thank you.
For the great talk.
I had a small question. So people have already shown that simple models of fermions hopping on the lattice do preserve non-invertible symmetries automatically, essentially. So maybe that's true for your model?
I would certainly hope so, yeah. It's a very interesting question. I think we don't know much now, but certainly the fact that we're seeing the string tension vanishing not only in the infinite volume limit, but also on a finite circle is evidence there might be something
Yeah, because on a
more.
finite circle, the only mechanism that's known
Exactly.
to protect the string tension is non-invertible symmetries.
Yeah, so one would hope we're seeing some remnant of it and that this is evidence of it, but yeah, I hope to know more in the future.
Just one comment. It seems like it's not just the string tension, but there is exact degeneracy of energy levels.
Yeah, so
Yeah,
there must be
yeah,
non-invertible symmetry, one would guess.
I tend to agree, yeah.
This theory also has another remarkable property. In the large n limit, if you impose periodic boundary condition, it satisfies volume independence. This is also called Eguchi-Kawai reduction. So if you go to large n limit in your setup, it may not be needed to take a very large. It may, for some purposes, this turns out to be more efficient.
Yeah, that brings me to another question that I should have mentioned on the last slide and I didn't, which is we're super limited in the number of colors right now. It becomes much harder to do it for even NC equals 4 is sort of the threshold of what I can even dream about. So I would love to have a formulation that can get us directly to the large n limit, but we're not there yet.
Okay.
I guess I have a question, follow-up on this large n limit question. So if I understand correctly, you do all the group theory before you put it on the lattice, right? So why is it difficult to go to large n?
Well, so what I didn't emphasize, which is that once we have this representation of these fermions in terms of invariant symbols, Once we want to compute Hamiltonian matrix elements, it's contractions of those invariant tensors, which give you 6J symbols. These 6J symbols are, to my knowledge, very difficult to compute efficiently. So that's one thing. The other thing is that even if we had a 6J symbols, there's just a really large number of sites, a large number of states for any even modest number of sites. Even for SU3, it's bad. So one would want an approach that sort of directly uses the large N limit in some way, but we don't have it yet.
Yes, Marine.
Thank you very much for the great talk. So numerically, what we're doing now is exact diagonalization.
That's
We
right.
want to move to tensor networks at some point.
That's right, yeah.
Thanks.
Yeah, one, I think, open question is to formulate the model on an open chain, and then there are, like what Grisha talked about for Schwinger model, then might become more possible to.
Yeah, and we can write this on an open chain. I think the key difficulty is, as Grisha mentioned in his talk, you want to use that U1 symmetry in DMRG to drastically improve the convergence. Here we want to use an SUNC symmetry, which is a little bit harder to get on the tensor network. In principle, it's possible.
Okay, if there are no more questions, let's thank Ross again.